Hello everyone, welcome to the Digital System Design class. In the last class we completed the module 1 and we have learned the concepts of the sequence of designing in combinational logic circuits and the different simplification techniques, okay, like the K-map and the Queen-McCluskey techniques are learnt in the module 1. So now we are going to move to the module 2, and the module 2 is analysis and design of combinational logic. So in this module we will going to apply the principles of what we have learnt in the module 1, okay, and then we will going to analyze and design of different combinational circuits. So in module 2 we will going to see the general approach of designing a combinational logic, okay. We already covered one problem in the last module, in the last part only. So whatever the problem what you have solved in the last, so covering the all the sequence, okay. So that is what the general approach actually we are going to see now actually, okay, and then we are going to see the analysis and design of the different combinational circuits. So decoders, encoders, adders, subtractors, comparators and programmable logic devices, okay, PLDs, okay, that we are going to be learning in this module, okay. So first let us see the what are the general approaches to designing of a combinational circuit. So the general approaches are, so develop a statement describing the problem to be solved. So whatever the problem we need to be solved, for that one let us describe a statement. So that is what a problem statement, okay. Next, based on the problem statement, construct the truth table. So then use the K-map or Queen-McCluskey technique to simplify the functions. So whatever the function will be there from the truth table, that will going to be simplified by using the any of the minimization technique. And then arrange the simplified equations to suit the logic primitive type to be used in the realized circuit. So whatever the simplified equations will be there, that need to be designed, that need to be implemented, okay. To then we need to arrange that one, so and we need to see the which logic gates are suitable. So implementing only using the NAND gates or only the NOR gates, okay, or we may able to realize the using the AND and OR logic, okay, as per our requirement, okay, we need to be realize the gates or switching equations, okay, and then we will going to have the final logic diagram. So these are the sequences, or we can say the general approaches to design a combinational logic, okay. So now let us take up some few problems to understand these sequences or these approaches. Already we have covered one problem in the module 1 only. We are going to see the few more problems over here actually, okay. The problem we have taken here is design a combinational circuit will multiply 2-bit binary numbers. So we need to design a combination logic circuit that will going to give a product of 2-bit numbers actually, okay. The each are 2-bit, two 2-bit numbers, that product should be produced by that circuit. That kind of logical circuit or a combination circuit we need to be designed. So there are two 2-bit numbers, actually binary numbers. So I will consider A and B are the two numbers and each are 2 bits. So I will consider A1, A0, and I will take similarly I will take B1, B0 for the another input, that is B, okay. Now we need to look on the how many number of output will be there. So first of all we need to construct the truth table, okay. Then for to constructing the truth table we need to know the how many number of inputs and how many number of outputs. As per the given data, so you will get to understand that one, there are 4 inputs. So 2 numbers each are 2-bit, so that's why we are going to have the 4 bits will be there, that's fine, okay. Then how many number of outputs will be there, that we need to be identified. When we need to multiply, so this is what the given is what statement multiply. So if you are multiplying the 2-bit data, okay, maximum we are going to get the 4-bit data. So output will be the 4-bit actually, okay. So we can understand that one. So if a 2-bit are there, means what are the possible values we have? 0 to 3, right? 0, 1, 2, 3. Similarly here also we can have 0, 1, 2, 3. So the maximum values are 3, 3, right? So when you multiplying the 3 into 3, you will get the 9. So that is the maximum value when multiplying the 2 bit. So 9 can be represented by the 1001, right? So that means 4 bits are enough to represent the output for this problem. Okay, so thus we identified the how many number of inputs and how many number of outputs. Let's construct the truth table. So let's write the truth table. So inputs A1, A0, B1, B0. Okay. So again, so there are 4 bits are there. So outputs. Let's represent the 4 bits are P0, P1, P2 and P3. Since we are doing a product actually, so I have taken a P0, P1, P2 and P3. So the truth table P0, P1, P2, P3. Okay. So let's construct the truth table. We need to multiply the 2 bit. So this is 0, 0, 1 bit, next 0, 0, 0 into 0, 0 into 1, 0 into 2, 0, 0, 0, 1, 0 is 2. Okay, next 0, 0, 1, 1. 0 multiply with 3. Similarly, 1 multiply with 0, 0, 1, 0, 1 like that. Correspondingly actually decimal values 0, 1, 2, 3, 4, 5. Let's continue there up to the 15. So that completes the truth table 0 to 15. Okay. So here I will going to write the decimal value. So the decimal number 0, 1. Okay. So now we need to write the output. So what we need to do? We need to multiply. Okay. So there 0 will multiply with 0. Next 0 with 1, 0 with 2. Similarly like this 2 with 2, 3 with 1, 3 into 3. Okay. Like that we need to multiply. So let's write the output as per the multiplication. 0 into 0, output will be 0, right? So that means product will be 0. 0 into 1, 0, because 0 multiply with any number will going to lead to 0. So let's write the output. 0 into 2, 3, 0. Next 1 into 0, again 0. Next 1 into 1, so 1. So output will be 0, 0, 0, 1. Okay, hope you understood. Now we need to multiply with 1 into 2. Like that we need to multiply for the 3 into 3. So 1 into 3, so that is 1 into 2, output is 2, 0, 0, 1, 0, 1 into 3, 3. Next 2 into 0 is 0, 2 into 1, 2, 2 into 2, 4. Next 2 into 3, 6. Next is 3 into 0 is 0. 3 into 1 is 3. Next 3 into 2, 6. And 3 into 3 is 9. So this is how we are going to get the product. Now we need to write the switching equations corresponding to the outputs. So here we have 4 outputs. So we are going to have the 4 switching equations and we are going to get the 4 K map, okay, for simplifications, and then we are going to have the logic circuits. Okay. So let's write the switching equations corresponding to the 4 outputs that are P0, P1, P2 and P3. So for the P0, that is equals to f of A1 A0, B1 B0, that is equals to, that means we have to write the switching equation. So we need to see the output. Wherever it will be 1, the corresponding decimal values will be written in a sigma notation. Okay. Here we are taking a minimal SOP expression. Okay, that means we are looking for the logic 1. Okay. So, there is summation of only one output is generated. So, the corresponding input combination is 15. So, that is P naught will be summation of 15. Similarly, let us consider the P1 f of A1 A naught B1 B naught equals to summation of. So, wherever the P1 will be generated, that means P1 is logic 1. So, we need to see the corresponding input and we need to write the equation. Okay. So, that is what here 10, 11 and the 14. So, similarly P2 equals to f of 6, 7, next 9, 11, 13, 14. Similarly, P3 equals to summation of 5, 7, 13, 15. So, this is how we are going to get the switching equations. Now, we need to write the K map and we need to simplify the C equation. Okay. So, we will write the K map for the P naught. For P naught, so 4 variable, so 16 cell K map will be there, and this is A1 A naught and here B1 B naught. Okay. Now, function is P15 will be the 1 and the remaining will be the 0, right. So, there is only one group. So, the group is what the only one group we can have, and the equations will be corresponding to that will be the P naught will be equals to the A1 A naught B1 B naught, right. So, that now let us move to the P1. For P1, so let us write the K map for the function P1. So, that is 10, 11 and the 14 are 1 and remaining are 0. Okay. So, let us group this. So, what are the possible groups? These two can be one group and these two are one more group, right. So, these are the only possible groups we can do. So, let us have the equation for the P1. So, P1 will be equals to, if you look for this group actually, so what are all the equations we can get? A1 A naught bar, and if you look for the B1 B naught, so B naught will be there, so that is B1. So, and the equation for this group is, okay, so A1 and here B1 B naught bar. Hope you understood, and I hope you know that when I am writing this one, because these are already covered in our last module itself. Okay. So, let us write the K map for the P2. Okay. So, as per the equation P2, 6, 7, 9, 11, 13, 14 will be 1 and remaining will be 0. So, if you are looking for the grouping, so these two can group, these two and these two have to group, right. So, the equation P2 will be equals to, so corresponding to this group, so we have a A1 B1 B naught bar plus corresponding to this group, okay, so A1 A naught bar and B naught bar plus for this group, okay, so A1 bar A naught and the B1 plus for this group, okay, 0 0 0 1, so that means A naught and B1 B naught bar. Now we will have the K map for the P3. Okay, so as per the P3, 5 7 13 15 will be 1, so 5 7 13 50 will be 1 and the remaining will be 0, so that means we will have only one 4 cell group will be there. According to that one, the simplified equation for the function P3, so that we are going to get as a 0 1 1 1, so that means A naught, next here 0 1 1 1, so that is B naught. Okay, so these are the 4 equations we have, P naught, P1, P2, P3. Now we need to design this one, we need to realize these equations by using the logic gates. So let's write the logic diagram for all these 4 equations. So these are the 2 equations we have. Let's design the logic diagram. Okay, so we have the inputs A1 A naught, B1 B naught, right, and we may have even its complement form also, right. So here only I will write that one. So this corresponds to the A1 bar, this corresponds to A1 and this thing corresponds to the A1 bar. Similarly A naught, A naught bar, B1 B naught bar, B1 bar, similarly B naught and B naught bar. Okay, so now let's write the logic diagram for the P naught, ANDing of A1 A naught B1 B naught. So this term here and this all are and together we are going to give the P naught. Okay, so now next P1, so A1 A naught bar, A1 A naught bar, next B1, this should be AND, next A1 B1 B naught bar, A1 B1 B naught bar, these 3 inputs will be AND and these 2 are summed, so that we are going to get the P1. Okay, so next is the P2, so A1 B1 B naught bar, A1 B1 B naught bar. Okay, next A1 A naught bar B naught bar, A1, so A naught bar, this is A naught bar and the B naught bar, this should be AND. Next A bar, A1 bar A naught B1, so A1 bar A naught and the B1, these 3 will be AND, and next is what the A naught B1 bar, B naught. Okay, so A naught, B1 bar, and next is B naught. These three, and all these are odd, and that will going to give the P2. And next P3, A naught, B naught. So this is A naught and the B naught are AND together, so that will going to give the P3. So this is the logic circuit will going to generate the multiplication of the 2 bits. Okay, so A1 A naught, B1 B naught. As per the truth table, if you give the inputs 0 0 0 1 like that multiplications, okay, so we are going to generate the output. Okay, so this is how the designing of an combinational circuit as per our requirements. Okay, so as per the problem statement given, we have constructed the combinational circuit that will going to multiply the two 2-bit binary numbers. Okay, so next problem is design a combinational circuit to output a 1 when an illegal BCD code occurs. Okay, first of all we need to understand what is a BCD code. So BCD code is the binary coded decimal. So binary coded decimal means we will have a for 0 to 9. So that means 0 0 0 to 1 0 0 1 9. So it will be a 4-bit actually. So 0 to 9 it will going to have the that is number is called as an BCD code. Okay. So here what we need to design a combination circuit to be output 1 when the illegal BCD code occurs. That means other than the BCD code is occurs means the output must be 1. If the BCD code occurs means output must be 0. Okay. That type of a combination circuit we need to be designed. So the how many number of inputs will be there? 4 bits, because the BCD codes are 0 to 9. So this 9 to implement a 9 we need a 4 bits. So the output will be the 4 bits. So inputs will be the 4 bits and only one output will be there. Okay. So let's have a truth table for this problem statement. Now the truth table will be 4 inputs and there will be 1 output. Okay. So the as usual I will write the decimal number. So decimal number 0001, sorry, truth table 0001. So 0, 1, 2. So the truth table. So as I already said, so BCD code will have the values from 0 to 9. So that means the inputs will be the 4 bit will be there. So that is 0 to 15. So in this 0 to 9 is the BCD code, right? Remainings are the non-BCD codes. So there is the question is what actually design a combination circuit to output a 1 when then illegal BCD code occurs. So what are the illegal BCD codes means in this 0 to 15? So 10 to 15 are illegal BCD, that means non-BCD values. So 0 to 9 are the BCD. So that means the circuit will go into output will be 0 for the up to 9, okay, and the remaining output will be 1 because these are the non-BCD values. So the BCD values will be added to 0, right? And the whichever the inputs are non-BCD values, then the output will be 1. So now we need to design a circuit that should be operate for this function. Okay. So as usual we constructed the truth table. Let's write the switching equation and let's write the logic diagram. Okay. So the y equals to f of a b c d and the summation of. So wherever the 1 will be there, we need to write the decimal values, that is 10, 11, so you can say 10 to 15. Okay. So let's have the K map corresponding to this. as per the given function 10, 11, 12, 13, 14, 15 are 1, remaining r will be 0. So now we need to make the group. So these 4 can be one group, right? And again these 4 can be make a one more group. So these 4 cells, right? So the equation y will be, so according to this equation, so it will be AB plus as per this group, so AC, right? Okay, let's have the circuit as per this simplified equation. So we have A, B, C, A, B and together next AC and R. These two will be R and that will going to give the Y. So that means this circuit will going to give the logic 1 when we have a non BCD code. So that means when we have a 10, 11, 12, 13, 14, the output will be 1. For the remaining inputs, the output will be a 0. Okay. So this is how we will going to design the combinational circuits. Okay. So now analyze and design the different combination circuits. So that is encoders, decoders, that we will going to take in the next class. Thank you.